Hi, my name is Hakbin Kim. I got my master's degree in computer engineering from Inha University. Today, I'll be presenting our work full of experts acquiring specialized knowledge in massive neural networks. Let's get started. Recently, the areas related to AI services have been getting a great deal of attention. But from the perspective of AI as a service provided on embedded devices, the process of training a model still takes too long to deliver it to users in real time. In addition, a resulting model is usually too generic and heavyweight. Hence, essentially goes through another training phase for model compression. And this makes it difficult to provide real-time AI services. So we propose a novel framework called Pool of Experts, which is a real-time model crunching system that can instantly build a specialized and lightweight model for a target query task, particularly in a way of train-free, data-free, and code-free. Next are notation and problem definition. First of all, large C is a set of all tasks, and it can be divided into n primitive tasks. HI is a primitive task, which is the smallest unit of task when C is split based on semantic similarity. Composite task Q is a user-requested task, which is a union set of multiple primitive tasks. MC is a pre-trained model to classify all the tasks we can handle and will be used as an oracle model. And MQ is a specialized model in composite task Q and requested by the user. At this time, the problem of our paper is to deliver model MQ to the user that meets the following conditions when given Oracle MC. First, MQ must be significantly smaller than MC. Secondly, although it is small, the accuracy must be similar to MC. Third, create a model MQ as fast as possible. Now, we are going to talk about some of the related works. The first branch of such works is knowledge distillation. The purpose of knowledge distillation is model compression for deployment. And the main idea of knowledge distillation is transferring the knowledge from a larger model to smaller model. In our paper, we also used basic CADE method, but the biggest difference is that our method extracts only some of the knowledge needed from the teacher model. Next is model specialization. The purpose of model specialization is to reduce inference time by building a small specialized model than a large oracle model. Recent studies use the method of selecting the best performing models with small architectures as candidates. These methods require additional training time, but our methods can generate specialized models after the pre-processing phase without additional training time. The last one is model unification. The purpose of model unification is merging heterogeneous models. Recently, CADE-based methods have been proposed, but they also require additional training time. Now, let me explain the method presented in this paper. The method is largely divided into two stages: pre-processing phase and service phase. Pre-processing phase is the process of decomposing knowledge of oracle models into multiple components. And service phase is the process of combining segmented components to create and deliver a user-requested model. Let's take a look at the process with the picture. First, it's pre-processing phase. Given the Oracle model, multiple components are extracted from the Oracle. At this time, you can think of the library as a common feature extractor. Also, think of expert as a component that acts as a specialized classifier for each primitive task. And by getting these components together and storing them in our framework, pool of experts, we complete the pre-processing phase. Next is the service phase. In the service phase, when a user requests a required task, only the components needed to perform the query task are retrieved from pool of experts. And then the model is generated and delivered to the user by simply assembling them without further training process. Let me now explain the specific principles of our proposed method. First of all, the library extraction part in the pre-processing phase. To extract the library, we create a student model that compresses the Oracle model using the existing KD method and use the S layer of the generated student model as the library. At this point, the trade-off of the accuracy and size will exist depending on the size of L. And next is the experts extraction. To this end, we presented conditional knowledge distillation. Conditional knowledge distillation is a technique that distills only knowledge of the task required without distilling the entire knowledge of the teacher model. We use this technique to train experts only for each primitive task. The entire loss of CKD consists of soft loss and scale loss. Soft loss is similar to existing KD loss. At this point, the difference is that we only extract the lossy values of the teacher model that correspond to the task we need and calculate the loss using only the corresponding sub-losses. By doing so, specialized knowledge can be extracted. And soft loss also prevents experts from becoming overconfident. As shown in the picture in the red dotted line, deep learning models show overconfidence in out-of-distribution images when trained using hard labels. In contrast, if trained through soft loss, we have low confidence for out-of-distribution images. The reason we need to solve this problem is that when we create a model through assembly in the service phase, if overconfident experts are generated, its classification problems can occur. Next is the scale loss. Scale loss is a loss used to solve lossy scale problems. Even if the problem of overconfident is solved through soft loss, as shown in figure A, if there is a difference in each lossy scale, as shown in figure B, additional misclassification can occur. Therefore, it is the scale loss that serves to match the lossy scale of the experts, which can further reduce the misclassification rate. Thanks to the losses described earlier, the overconfident and logic scale problems have been resolved. So the service space can generate a model that performs the required task requested by user by simply assembling library and experts without additional training process. Next is the experimental results. We used two data sets, C400 and Tiny ImageNet, in the experiment. And as an architecture, we used the modified wide resonance series, and we experimented on every combination using 6 primitive tests on each data set. The experiment consists largely of model specialization and consolidation. In the model specialization part, among the specialization methods, our CKD method achieves the best accuracy, pretty close to the level of oracles, despite its tiny target models. In particular, the parameters are about 100 times less used than the oracle model. And figure 5 presents an example to see how those highest confidence values are distributed, all of which are from out-of-distribution samples. It is clearly observed that transfer as well as scratch is too confident about out-of-distribution samples in that a confidence value larger than 0.9 appears most frequently. Thus, as mentioned before, even if we perform transfer learning from Oracle to obtain a specialized model, the resulting model could be overconfident about samples irrelevant to it. As opposed to that, in the model specialized by CKD, the most frequent confidence value lies in the range from 0.3 to 0.4, implying not too confident about classes they do not know. When using either only soft loss or CKD loss as a whole. This confirms the fact that soft loss effectively informs the target model about unknown classes in the process of distillation. We measure the task-specific accuracy for generic models as in the pre-processing phase and varied the number of primitive tasks in queue from 2 to 5 for each accuracy value. We report the average over all the combinations of as many primitive tasks used in queue. In terms of the overall accuracy, it is surprisingly observed that POE beats most of the training methods except for CKD, even though POE does not involve any training process. And our CKD method still shows almost always the highest accuracy as it is in the specialization test. And figure 7 represents the average training time. When each correct composite task consists of more and more primitive tasks, the average training time of all the methods to achieve their best accuracy drastically increases except for POE. Thus, when a user requests a variety of composite tasks, only POE is suitable for a real-time service. Finally, our contributions are as follows. We present Pool of Experts, which is a novel framework for the real-time model querying system, and devised conditional knowledge distillation in order to extract only the specialized knowledge from a pre-trained neural network. Lastly, we propose train-free knowledge consolidation, so that we can merge multiple experts into a single unified model without any training process. That's all for my presentation. Thank you for your attention.